Science has mapped galaxies billions of light years away. It has measured particles smaller than atoms and traced the history of the universe back to its earliest moments. Yet after centuries of discovery, a strange problem remains. There appears to be a region where reality itself becomes inaccessible, a place where observation fails, prediction breaks down, and the rules that describe the universe lose their clarity. The deeper scientists investigate, the more they encounter a boundary that refuses to reveal what lies beyond it. Tonight we explore one of the most unsettling possibilities in modern physics, that reality may contain a blind spot, and everything we know exists on only one side of it. Human beings often assume that seeing is a direct connection to reality. We open our eyes, observe the world around us, and naturally feel that what we experience represents what actually exists. Mountains appear solid, the sky appears continuous, the stars seem scattered across a vast cosmic distance. Every moment of daily life reinforces the belief that observation reveals reality as it truly is. Yet one of the most important discoveries in science is that observation does not simply reveal the universe, it filters it. The idea sounds strange because perception feels effortless. Light enters the eyes, sounds enter the ears, information reaches the brain, the world appears, the process seems straightforward. But beneath this familiar experience lies a hidden limitation that shapes everything we know. Human observation is not a window that opens fully onto reality. It is a narrow channel through which only a small fraction of existence becomes visible. Consider the electromagnetic spectrum. Human eyes can detect only a tiny range of wavelength. The colors we see represent a narrow band of light surrounded by enormous regions that remain invisible. Radio waves pass through the atmosphere without being seen. Infrared radiation surrounds every warm object. Ultraviolet light arrives from the sun. X-rays and gamma rays move through the universe carrying information about violent cosmic events. All of these forms of light are real. All of them exist around us at this very moment. Yet without specialized instruments, human beings would never know they were there. Reality extends far beyond what sight reveals. This realization immediately changes how we think about observation. If entire regions of the electromagnetic spectrum remain hidden from ordinary perception, what else might be concealed? Every scientific instrument humanity has ever created has answered this question in the same way. Telescopes revealed galaxies invisible to the naked eye. Microscopes uncovered worlds smaller than imagination once allowed. Particle detectors exposed structures hidden within atoms. Again and again, technology has shown that reality contains layers existing beyond direct observation. Yet every new instrument introduces a deeper mystery. Each time we extend our ability to observe, we discover not only new information but also new boundaries. The horizon moves farther away, but it never disappears. There is always another limit waiting beyond the previous one. Imagine standing on a shoreline looking out across the ocean. The horizon appears to define the edge of the visible world. As you travel forward, the horizon moves with you. It never allows itself to be reached. Observation behaves in a similar way. Every advance in science expands the visible territory of reality, yet new frontiers immediately emerge beyond it. The universe continuously reveals more of itself, while preserving regions that remain inaccessible. This pattern suggests something profound. The limits of observation are not merely practical limitations caused by imperfect technology. Some limits may be woven into the structure of reality itself. Modern physics repeatedly encounters situations where observation becomes fundamentally constrained. Quantum mechanics provides one of the most famous examples. Certain properties of particles cannot be measured simultaneously with unlimited precision. The more accurately one quantity is determined, the less precisely another can be known. This is not a flaw in our instruments, it appears to be a feature of nature itself. Reality places boundaries on what can be observed. The implications are extraordinary. For centuries, many scientists assumed that perfect knowledge was theoretically possible. Given sufficient information and sufficiently powerful tools, the universe could be understood completely. Quantum physics challenged that assumption. It revealed a world in which uncertainty is not merely a temporary obstacle. Uncertainty may be built into the fabric of existence. Even at larger scales, similar limitations appear. Astronomers studying distant galaxies face a fundamental restriction imposed by the speed of light. Every observation looks into the past. When a telescope observes a galaxy millions of light years away, it does not see the galaxy as it exists now. It sees light that began its journey millions of years ago. The farther we look into space, the farther we look backward in time. Observation never provides direct access to the present state of the distant universe. This means that even our most advanced observations are incomplete. We are always receiving delayed information. Reality arrives through signals that require time to travel. What we observe is not the universe as it is. It is the universe as it was when the information began moving toward us. The deeper scientists investigate, the more they encounter this hidden structure. Observation is not immediate contact with reality. It is a process involving distance, delay, interpretation, and limitation. Every measurement represents a conversation with the universe conducted through intermediaries. The situation becomes even more fascinating when we consider the role of the brain. Human perception is not a passive recording system. The brain actively constructs experience. It filters incoming information, identifies patterns, fills gaps, and creates a coherent picture of the world. Much of what we experience is not a direct representation of reality, but an interpretation generated by neural processes. This can be demonstrated through simple visual illusions. The brain often creates shapes, colors, or movements that do not physically exist. These examples reveal an important truth. Observation is not merely receiving information. Observation involves creating meaning from information. The consequence is difficult to ignore. Everything we know about the universe reaches us through layers of filtering. First, the limits of physical reality restrict what information becomes available. Then the limits of our instruments determine what can be measured. Finally, the limits of perception influence how that information is interpreted. Something remains hidden. This hidden quality does not make science unreliable. In fact, recognizing these limits is one of science's greatest strengths. Scientific progress often begins when researchers identify boundaries that previous generations overlooked. The history of discovery is, in many ways, the history of expanding observation beyond its apparent limits. Yet, no matter how far observation advances, one unsettling possibility remains. Some regions of reality may never become visible. Some information may remain permanently inaccessible. There may exist aspects of the universe that cannot be observed because observation itself cannot reach them. This possibility leads directly to the concept of a blind spot in reality. Not a blind spot created by ignorance. Not a blind spot created by insufficient technology. A blind spot created by the structure of existence itself. A region where observation encounters a boundary it cannot cross. A region where information fails to arrive. A region where reality continues beyond the edge of what can be seen, measured, or understood. And if such a boundary truly exists, then the most important question is no longer what we can observe. The most important question becomes what remains hidden beyond the limits of observation itself. Human beings often treat measurement as the closest thing to certainty. When something can be measured, it feels real. A distance can be calculated. A temperature can be recorded. The mass of a planet can be estimated. The age of a star can be determined. Measurement gives science its power because it transforms observation into knowledge. It allows patterns to be compared, predictions to be tested, and theories to be refined. Yet hidden inside every measurement is a strange limitation that most people never think about. No measurement ever captures the whole of reality. Every act of measuring reveals something while leaving something else unseen. This may seem like a practical problem. Instruments have limits. Telescopes can only detect certain wavelengths. Microscopes can only magnify so much. Sensors possess finite precision, but the deeper scientists investigate, the more they discover that the problem runs far deeper than technology. The act of measurement itself appears to create boundaries around what can be known. Imagine standing in a dark room with a flashlight. Wherever you point the beam, details become visible. Objects emerge from the darkness. Shapes become recognizable. Information appears. Yet the moment one area is illuminated, countless other regions remain hidden. The flashlight does not reveal the entire room. It selects a portion of it. Measurement behaves in a surprisingly similar way. Every measurement focuses attention on particular features of reality while leaving other features outside its reach. Consider something as simple as measuring the speed of a moving object. The measurement provides valuable information. It tells us how quickly the object changes position. Yet the measurement does not tell us everything. It does not automatically reveal every force acting upon the object. It does not reveal every interaction occurring within its structure. It does not describe every relationship connecting it to the rest of the universe. The result is useful, but it is incomplete. This incompleteness is not unusual. It is built into the nature of knowledge itself. Whenever scientists measure something, they must decide what to measure. That decision creates a frame. It defines what information will be collected and what information will remain outside the scope of observation. Reality is always larger than the measurement describing it. The issue becomes even more interesting when we think about maps. A map provides information about a landscape. It may show roads, rivers, mountains, and cities. The map can be incredibly accurate and useful. Yet no map contains every detail of the territory it represents. It cannot include every grain of sand, every leaf, every insect, and every microscopic feature. If it attempted to do so, the map would become as large and complex as the territory itself. A useful map must simplify reality. Measurements perform a similar function. They create manageable descriptions of systems that are vastly more complicated than the numbers used to represent them. Every measurement is a reduction. Every measurement extracts certain information while leaving the rest behind. For centuries, this limitation seemed manageable. Scientists assumed that enough measurements could eventually reveal everything important about a system. If one measurement left something unseen, additional measurements could fill the gaps. The universe appeared to be a puzzle that could be solved piece by piece. Then quantum physics arrived and changed the situation completely. At the quantum level, scientists encountered a limitation unlike anything they had seen before. Certain properties of particles cannot be measured simultaneously with unlimited precision. The more accurately one property is known, the less accurately another can be determined. This principle is not caused by faulty instruments. It appears to be woven into the structure of reality itself. The implications are extraordinary. Imagine trying to determine both the exact position and exact motion of a particle. Classical intuition suggests there should be no problem. If the particle exists, then its properties should simply be there waiting to be measured. Yet quantum mechanics reveals something more subtle. The act of measurement becomes entangled with the information being measured. Reality refuses to reveal everything at once. This discovery forced scientists to reconsider what measurement actually means. Before quantum theory, many people imagined measurement as a passive activity. An observer looks at reality and records what is already there. Quantum mechanics suggests a more complicated relationship. Observation is not always passive. The process of measurement can influence the system being observed. Imagine attempting to photograph a tiny object in complete darkness. To see it, light must be directed toward it, yet the light itself interacts with the object. The very act of making the object visible changes its condition. At ordinary scales, this effect is insignificant. At quantum scales, it becomes impossible to ignore. The result is remarkable. Every measurement carries a trade-off. Gaining information in one area may limit information in another. Reality seems unwilling to surrender a complete description of itself through any single act of observation. This pattern extends beyond quantum mechanics. Astronomers face similar challenges when studying the cosmos. Every observation of a distant object depends upon light reaching Earth, yet the light takes time to travel. When scientists observe a galaxy millions of light years away, they do not see the galaxy as it exists now. They see ancient information that began its journey millions of years earlier. The measurement reveals something real. It conceals something equally important. The galaxy's present condition remains unknown. No matter how powerful the telescope becomes, it cannot eliminate the delay created by distance. The observation always arrives from the past. Every cosmic measurement leaves part of reality unseen. The deeper we look into space, the farther we look backward in time. The universe reveals its history while withholding its current state. Even closer to home, similar limitations appear. Consider weather forecasting. Scientists collect enormous amounts of data from satellites, sensors, and computer models. These measurements provide valuable insights into atmospheric conditions, yet tiny uncertainties remain. Small pieces of missing information can eventually grow into significant differences in predictions. The atmosphere contains more complexity than any measurement can fully capture. This principle appears throughout nature. Reality always contains more detail than observation can exhaust. Every measurement creates a useful description. No measurement becomes the thing itself. The mystery becomes even deeper when we consider information. Modern physics increasingly treats information as a fundamental aspect of reality. Matter carries information. Energy carries information. Quantum states carry information. The universe appears filled with informational relationships operating across every scale. Yet whenever information is measured, some portion remains inaccessible. Not because it ceases to exist, because the act of measurement selects only certain aspects of the larger structure. Imagine reading a single chapter of a novel. The chapter provides meaningful information. Characters appear, events unfold, themes emerge, yet the chapter does not contain the entire story. Understanding remains partial until larger relationships become visible. Measurements may function in a similar way. Each one reveals a fragment of a much larger reality. The fragment is real. The fragment is valuable. The fragment is never complete. This realization carries profound consequences. It means that ignorance is not merely a temporary condition waiting to be eliminated. Some forms of incompleteness may be built into the process of observation itself. Every attempt to know reality creates a boundary around what is known. Beyond that boundary, something remains hidden. This hidden region does not necessarily contain magical answers or undiscovered dimensions. It simply represents the part of reality left outside the frame of the measurement. The existence of such hidden regions becomes increasingly important as science approaches its deepest questions. What lies beyond the observable universe? What happens inside a black hole? What existed before the earliest moments we can describe? What structures exist beneath space-time itself? Again and again, researchers encounter situations where measurement reaches a limit. The universe continues. Observation does not. And that may be the most important lesson hidden inside every measurement. Whenever science illuminates a portion of reality, a shadow appears alongside it. Every answer creates a new boundary. Every discovery reveals another horizon. Every measurement leaves something unseen. And somewhere within those unseen regions may lie the blind spot that reality has never fully revealed. The universe appeared understandable. The stars moved across the sky in predictable patterns. Objects fell toward the ground. Seasons arrived and departed. Nature seemed to follow rules that could be observed, studied, and eventually explained. As science developed, this confidence grew stronger. Each century brought discoveries that expanded humanity's understanding of reality. Invisible forces became measurable. Distant worlds became observable. Matter itself revealed hidden structures beneath its surface. It often seemed as though every mystery would eventually surrender to investigation. Yet as physics pushed deeper into the foundations of existence, something unexpected happened. The universe did not become clearer in every direction. Scientists began encountering regions where their most successful theories stopped providing reliable answers. These were not places where observations were merely difficult. They were places where the conceptual framework of physics itself started to lose clarity. The equations remained powerful, but their ability to describe reality began to weaken. Familiar ideas such as space, time, motion, and causality no longer behaved in ways that made intuitive sense. These regions represent some of the most fascinating frontiers in modern science because they reveal a remarkable truth. The universe contains boundaries where our understanding reaches its limits long before reality does. To appreciate this, imagine using a map while exploring unfamiliar territory. The map works perfectly across most of the landscape. Roads appear where expected. Landmarks match their descriptions. Navigation feels straightforward. Then suddenly the map ends. Beyond its edge, the territory continues, but the guidance disappears. The problem is not that the world stops existing. The problem is that the map no longer describes it. Physics encounters similar situations. The laws that explain everyday phenomena work extraordinarily well within their domains. They predict planetary motion, electrical interactions, chemical reactions, and countless other processes with astonishing accuracy. Yet there are regions where the map begins to fade. One of the most famous examples involves black holes. A black hole forms when an enormous amount of matter collapses into a tiny region of space. The resulting gravitational field becomes so powerful that not even light can escape once it crosses a boundary known as the event horizon. Outside the event horizon, physics remains reliable. Scientists can calculate trajectories, predict behavior, and model interactions with impressive precision, but deeper inside, the picture becomes increasingly uncertain. According to current equations, the collapse eventually leads to a singularity, a region where density becomes infinite and the mathematics breaks down. Most physicists do not believe that actual infinities exist inside nature. Instead, singularities are often interpreted as signs that the theory has reached its limits. The equations are telling us something important. They are telling us that our description of reality has become incomplete. The black hole does not stop existing. Reality continues. Understanding does not. This distinction lies at the heart of the blind spot mystery. The universe repeatedly presents situations where reality appears to extend beyond the reach of existing explanations. Another example emerges when scientists attempt to understand the earliest moments of the universe. Modern cosmology allows researchers to reconstruct cosmic history with extraordinary detail. Observations of background radiation, galaxy distributions, and cosmic expansion reveal information about events that occurred billions of years ago. Scientists can trace the evolution of the universe back to an astonishingly early stage. They encounter a boundary. As calculations approach the earliest fractions of a second after the Big Bang, the conditions become so extreme that known theories begin to conflict. Gravity becomes enormously important at scales where quantum effects also dominate. General relativity and quantum mechanics, the two most successful theories in modern physics, cease to cooperate. Each theory works beautifully within its own domain. Together, under extreme conditions, they produce contradictions. The result is a region where physics loses clarity. The universe possesses a history, yet part of that history remains hidden behind a conceptual barrier. Scientists can approach the boundary, they cannot yet cross it. The same pattern appears in attempts to understand space-time itself. Space and time were treated as the fundamental stage upon which reality unfolds. Einstein revolutionized this picture by showing that space and time form a unified structure known as spacetime. This framework transformed physics and remains one of the most successful ideas ever developed. Yet modern research increasingly suggests that spacetime may not be fundamental. Certain approaches to quantum gravity propose that space and time emerge from deeper structures. If this is true, then spacetime resembles a surface phenomenon rather than the ultimate foundation of reality. The implication is extraordinary. The very framework through which we understand existence may itself arise from something deeper. And if space-time emerges from more fundamental processes, then there must exist a level where ordinary concepts of distance, duration, and location lose their meaning. Physics reaches another region where clarity fades. The challenge becomes even more profound in the quantum world. Quantum mechanics remains one of the most accurate scientific theories ever created. Its predictions have been confirmed repeatedly through experiments of astonishing precision. Yet despite its success, physicists continue debating what the theory actually says about reality. Particles behave like waves. Waves behave like particles. Systems appear to occupy multiple possibilities before measurements occur. Entangled particles display correlations that challenge ordinary intuition. The mathematics works. The interpretation remains uncertain. This creates a remarkable situation. Scientists possess equations capable of predicting outcomes with extraordinary accuracy, yet the deeper meaning behind those outcomes remains unclear. Reality behaves in ways that resist familiar descriptions. The theory succeeds. Clarity does not always follow. Another strange region appears whenever information becomes inaccessible. Imagine trying to understand a conversation while hearing only every 10th word. The fragments provide clues, but the full meaning remains hidden. In some areas of physics, researchers encounter similar limitations. Information essential for a complete description becomes unreachable. Black holes create this problem. Cosmic horizons create this problem. Even the finite speed of light creates this problem. The universe contains regions from which information cannot currently reach us. Reality may continue there exactly as it does elsewhere, but observation loses access. Knowledge encounters a boundary. This realization reveals something important. The limits of physics are not always caused by intellectual failure. Sometimes the structure of reality itself creates barriers. The universe does not guarantee complete access to its own contents. Certain regions remain hidden not because scientists lack effort or creativity, but because information cannot easily cross the boundaries separating them from observation. Perhaps the most fascinating aspect of these strange regions is that they often appear precisely where our understanding becomes most ambitious. The closer scientists move toward ultimate questions, the more frequently clarity begins to dissolve. What existed before the earliest observable universe? What happens inside a black hole? What creates space-time? How does quantum reality become the world we experience? What lies beyond the observable cosmos? Again and again, the path leads toward regions where established concepts become uncertain. The universe seems to possess a horizon, not only in space, but also in understanding, a point beyond which familiar explanations lose their power. This does not mean the search has failed. Quite the opposite. Throughout history, boundaries of understanding have often marked the beginning of new discoveries, rather than the end of investigation. Every major revolution in science emerged because someone encountered a region where existing ideas stopped working. The breakdown itself became a clue. The absence of clarity pointed toward deeper truths waiting to be uncovered. Yet the existence of these regions carries a profound lesson. Reality is under no obligation to remain understandable according to human intuition. The universe existed long before human beings appeared. Its deepest structures may operate according to principles far removed from everyday experience. The places where physics loses clarity remind us that knowledge has edges. Beyond those edges, reality continues. And somewhere within those hidden regions may lie the blind spot that modern science has not yet learned how to see. Everything human beings know about the universe comes from information. Every scientific discovery, every observation, every equation, and every theory depends upon one simple fact. Information must travel from the thing being observed to the observer. Light from distant stars reaches telescopes, sound waves reach the ears, signals reach instruments, data reaches scientists. Without this transfer, knowledge becomes impossible. We do not interact with reality directly. We interact with information about reality. This idea sounds obvious at first, yet it carries a consequence that is both profound and unsettling. If information can reach us, we can learn about something. If information cannot reach us, that part of reality becomes inaccessible. It may continue to exist, it may continue to evolve. Entire processes may unfold within it. Yet from our perspective, it effectively disappears behind a curtain we cannot cross. This creates one of the deepest blind spots in all of physics. The universe is not divided merely into what exists and what does not exist. It is divided into what can send information to us and what cannot. The distinction changes everything. Imagine standing in a vast city during a power outage. Beyond your immediate surroundings, entire neighborhoods continue to exist. Streets remain where they were, buildings remain standing, people continue their lives. Yet without light or communication, those regions become inaccessible to you. The city has not vanished. Your access to information about it has vanished. Reality behaves in a surprisingly similar way. The universe contains regions where information travels freely, and regions where information encounters limits. As long as information can reach us, science can investigate. Once that flow stops, knowledge reaches a boundary. This becomes easier to understand when we consider light. Whenever astronomers study the cosmos, they are studying information carried by light. Every galaxy photographed by a telescope is known only because photons completed an extraordinary journey across space. Some of those photons traveled for millions of years, others traveled for billions. They carry messages from distant regions of the universe. Without those photons, the galaxies would remain invisible, not because they do not exist, because no information about them would arrive. This means that visibility is not determined solely by existence. It is determined by communication. The universe must deliver information before observation becomes possible. At everyday scales, this process feels effortless. We rarely think about it. Light reflects from objects around us and reaches our eyes almost instantly. The transfer happens so quickly that reality feels immediate. Yet the deeper scientists investigate, the more they discover that information obeys strict rules. Most importantly, information cannot travel infinitely fast. According to modern physics, the speed of light represents a fundamental limit. No signal carrying information can exceed it. This restriction may sound technical, but it has enormous consequences. Imagine observing the sun. The sunlight reaching Earth left the sun approximately 8 minutes earlier. If the sun were somehow altered, Earth would not know immediately. Information about the change would require time to arrive. The same principle applies everywhere in the cosmos. Every observation involves delay. Every measurement involves waiting. Every act of seeing depends upon information completing a journey. The farther away something is, the older the information becomes. This realization transforms our understanding of observation. When astronomers observe distant galaxies, they are not seeing those galaxies as they exist right now. They are seeing ancient information. Some of the light reaching Earth tonight began its journey before human civilization existed. Some began traveling before the first humans appeared. Some come from a time when Earth itself looked completely different. The universe we observe is partly a historical record. Reality arrives through messages from the past. This creates an extraordinary situation. There is always a gap between what exists and what we know. Information must cross that gap, and sometimes it cannot. One of the most dramatic examples appears in black holes. A black hole forms when gravity becomes so powerful that escape becomes impossible beyond a certain boundary known as the event horizon. The event horizon is not a physical wall. A spacecraft crossing it would not strike a barrier. Yet something remarkable happens there. Once information crosses the event horizon, it can no longer return to the outside universe. Light cannot escape. Signals cannot escape. Messages cannot escape. Information becomes trapped. From the perspective of an external observer, an entire region of reality suddenly falls beyond direct access. The black hole may contain matter. It may contain energy. Complex processes may occur inside it. Yet information about those processes can no longer reach us. This is one of the clearest examples of a blind spot in reality. The region exists. Physics predicts its existence. Observation loses access to it. The universe continues beyond the informational boundary. Knowledge does not. The implications are astonishing. People imagined ignorance as a temporary problem. With better instruments and more advanced theories, anything could eventually be understood. Black holes challenge that assumption. They reveal situations where information itself becomes inaccessible. The obstacle is not technological. The obstacle is fundamental. Reality contains regions from which information cannot return. The same idea appears at the largest scales of the cosmos. Because the universe is expanding, distant galaxies are moving away from one another. Some regions are receding so rapidly that light emitted today may never reach us. This does not mean those regions cease to exist. It means information from them may never arrive. They occupy portions of reality permanently beyond observation. Even if humanity survives for billions of years and develops unimaginable technology, certain regions may remain inaccessible because the information simply cannot cross the expanding cosmic distance separating us from them. The universe contains territories beyond communication, not hidden by darkness, hidden by the structure of space-time itself. This possibility forces us to rethink what knowledge means. We often assume that reality consists of everything that exists. Science reveals a more subtle picture. Reality consists of everything that exists, but knowledge consists only of what information can reveal. The two are not identical. Existence is larger than observation. The distinction becomes even more profound when we consider quantum physics. At the quantum level, information plays a central role in how reality behaves. Some physicists now believe that information may be more fundamental than matter itself. Quantum states, entanglement, and probability all revolve around informational relationships. Yet quantum systems also reveal limits. Certain information cannot be extracted without altering the system. Certain properties cannot be known simultaneously with arbitrary precision. Again and again, nature imposes boundaries. Information exists. Access does not always follow. The deeper we investigate, the more reality begins to resemble an enormous informational landscape. Some regions communicate freely, some communicate partially, some appear permanently disconnected. The blind spot emerges wherever information fails to cross the boundary. And perhaps the most unsettling aspect of this mystery is that we never directly perceive the missing information. Human beings experience only what arrives. We see the message. We do not see the messages that never reached us. Imagine reading a book while entire chapters have been removed. If you never knew the missing chapters existed, the gaps might remain invisible. You would build your understanding from the information available. Reality may be presenting a similar challenge. The universe may contain entire regions of existence that never contribute information to our observations. They become silent, not empty, not non-existent, silent. This possibility changes the meaning of the blind spot entirely. The blind spot is not simply a place where knowledge has not arrived yet. It may be a place where knowledge cannot arrive, a region separated from observation by boundaries that information cannot cross. And if such regions exist, then one uncomfortable possibility follows. The universe we observe may represent only a fraction of reality, beyond the limits of communication, beyond the reach of light, beyond the boundaries where information can travel. Existence may continue in ways we cannot witness, measure, or describe. Reality may be vastly larger than the portion that speaks to us. And somewhere beyond those silent boundaries, hidden behind the limits of information itself, the universe may be carrying out processes that science has never been able to observe. Processes occurring inside the blind spot. Processes that remain invisible not because they are small or distant, but because their information can no longer reach us at all. A powerful idea in science is the belief that if something exists, it can eventually be observed. Human progress has often reinforced this assumption. Mountains hidden beyond oceans were eventually discovered. Planets invisible to the naked eye were eventually detected. Galaxies beyond imagination were eventually photographed. Each generation pushed farther into the unknown and found that the universe was willing to reveal more of itself. This history created a natural expectation that every mystery is temporary and every hidden region is simply waiting for better technology. Yet modern cosmology has revealed a far more unsettling possibility. Some parts of reality may remain inaccessible, not because humanity lacks sufficient knowledge, but because the structure of the universe itself places boundaries around what can ever be observed. These boundaries are known as cosmic horizons. The word horizon usually refers to the distant line where the earth and sky appear to meet. As a person walks toward it, the horizon moves farther away. It never allows itself to be reached. The visible world always ends at a boundary beyond which new territory remains hidden. Cosmic horizons function in a similar way, but on a scale so vast that it challenges ordinary intuition. They mark regions where observation itself encounters limits. Beyond those limits, reality may continue indefinitely, yet information from those regions can never fully reach us. To understand why this happens, we must first remember that every observation depends upon information. Light, radio waves, gravitational signals, and other forms of communication carry knowledge across space. Without information, observation becomes impossible. The universe does not reveal itself directly. It reveals itself through messages traveling from one location to another. This simple fact creates an extraordinary consequence. Because information travels at a finite speed, every observer exists inside an informational bubble. No one can instantly access every event occurring throughout the cosmos. Every observation is limited by the distance information can travel and the time available for it to arrive. Imagine standing in the center of an enormous forest at night. Your lantern illuminates only a small region around you. Trees beyond the light remain hidden. They continue to exist. They may stretch for miles in every direction. Yet your awareness remains confined to the information reaching your eyes. The observable universe functions in much the same way. Humanity occupies a position within a vast cosmic sphere defined by the distance light has been able to travel since the beginning of cosmic expansion. Everything inside this sphere can, in principle, send information to us. Everything beyond it remains inaccessible because its signals have not had enough time to arrive. This does not mean that reality ends at the boundary. The boundary belongs to observation. Reality itself may extend far beyond it. Many cosmologists suspect that the universe continues well beyond the observable region. The observable universe may represent only a tiny fraction of a much larger structure. Yet because information from those distant regions has never reached us, science cannot directly investigate them. The distinction is profound. Humanity often speaks about the observable universe as though it were the universe itself. In reality, it is merely the portion available to observation. Beyond that horizon may lie additional galaxies, additional structures, and perhaps regions so distant that their light will never arrive. The deeper scientists explored cosmic expansion, the stranger this picture became. During the 20th century, astronomers discovered that the universe is expanding. Galaxies are not simply sitting motionless in space. On the largest scales, space itself is stretching. Distances between galaxies increase over time. This discovery transformed cosmology. It also introduced a remarkable consequence. Because the universe is expanding, some galaxies are moving away from us so rapidly that their light struggles to overcome the growing distance. The farther away a galaxy becomes, the more difficult communication becomes. In some cases, the expansion of space creates a situation where information emitted today may never reach Earth, no matter how long humanity waits. This means that parts of the universe are gradually disappearing from observational reach, not because they are vanishing, not because they are being destroyed, because the expanding structure of spacetime itself prevents information from crossing the gap. The universe contains regions that are effectively drifting beyond communication. This realization changes how we think about knowledge. Many people imagine ignorance as a temporary condition that disappears with enough effort. Cosmic horizons reveal a different possibility. Certain forms of ignorance may be permanent because the information required to eliminate them cannot arrive. Reality may contain territories forever separated from observation. This idea becomes even more fascinating when we consider the early universe. When astronomers observe the oldest light ever detected, known as the cosmic microwave background, they are looking back to an era when the universe was vastly younger than it is today. This radiation provides an extraordinary glimpse into cosmic history. Yet even here, a horizon appears. Before a certain point, the universe was opaque. Light could not travel freely. Conditions were so dense and energetic that photons constantly interacted with matter. Information from earlier periods remains hidden behind this barrier. The cosmic microwave background represents a kind of informational wall. It reveals much. It conceals more. Scientists can infer certain details about earlier epochs, but direct observation becomes impossible. Once again, the universe presents a boundary where knowledge encounters a limit. What makes these horizons particularly important is that they reveal a blind spot built directly into reality. The blind spot is not caused by poor instruments. It is not caused by lack of intelligence. It is not caused by insufficient effort. The blind spot emerges because information itself obeys physical laws. The universe places restrictions on communication, and wherever communication becomes impossible, observation ends. The concept becomes even more intriguing when we compare cosmic horizons to black holes. A black hole contains an event horizon, a boundary beyond which information cannot escape. Cosmic horizons operate according to a similar principle, although the underlying mechanisms differ. In both cases, the observer encounters a region that exists yet cannot fully communicate with the outside world. The parallel is difficult to ignore. At vastly different scales, the universe repeatedly creates boundaries separating what can be known from what cannot. These boundaries suggest that reality may be fundamentally larger than observation. Every scientific model, every map of the cosmos, and every description of existence is constructed from information that successfully reached us. Yet reality itself is under no obligation to restrict itself to the regions we can access. Imagine reading only a few chapters from an enormous book, while knowing that countless additional chapters remain sealed forever. The chapters you possess may reveal meaningful patterns. They may even allow you to infer aspects of the larger story. Yet uncertainty remains because the complete narrative lies beyond reach. Humanity may occupy a similar position within the cosmos. The observable universe may represent a fragment of a larger reality whose full structure remains hidden behind horizons. This possibility carries profound philosophical implications. People often assumed that the universe was designed to be understandable. Cosmic horizons challenge that assumption. They suggest that some aspects of existence may remain permanently inaccessible, regardless of technological progress. The challenge is not merely practical, it is structural. Reality contains regions where information cannot cross. Knowledge depends upon information, therefore knowledge encounters boundaries. And yet these boundaries reveal something surprisingly hopeful. Every horizon discovered throughout history has expanded humanity's understanding. Horizons do not merely conceal, they also define the frontier of exploration. They show us where current understanding ends and where deeper questions begin. The observable universe itself was once unimaginable. Galaxies beyond our own were once unknown. The expansion of space was once undiscovered. Each breakthrough revealed that reality was larger than expected. Cosmic horizons continue this tradition by reminding us that the visible universe is not the whole story. Somewhere beyond the regions illuminated by ancient starlight, beyond the limits of communication, beyond the reach of observation, reality continues its existence without interruption. Galaxies may drift through darkness, structures may evolve, events may unfold. The universe continues regardless of whether information about those events ever arrives. And that realization brings us closer to the central mystery of the blind spot. Because if cosmic horizons divide the observable from the unknown, then reality may already extend beyond every map science has created. The visible cosmos may not represent the full universe. It may represent only the portion willing or able to speak to us. Everything beyond the horizon remains silent, not because nothing exists there, but because the information needed to reveal it can no longer cross the boundary that separates knowledge from the unknown. The most remarkable feature of human experience is that reality feels complete. When you look around the room you are in, nothing seems missing. The walls appear solid. The objects around you seem fully present. The sounds reaching your ears feel like a complete representation of your surroundings. The world appears whole, continuous, and self-contained. This impression is so convincing that most people never question it. We naturally assume that what we experience is reality itself, yet one of the deepest discoveries in science suggests something very different. The completeness we experience may be, at least in part, an illusion created by the way information reaches us and the way the mind organizes that information. This does not mean the world is fake. It does not mean reality is imaginary. The universe certainly exists independent of human perception. The deeper point is that our experience of reality is constructed from limited information. Because that construction works so effectively, it creates the powerful impression that nothing important is missing. In truth, vast regions of existence may remain outside awareness while the mind continuously presents a finished picture. To understand how this happens, imagine reading a novel with several chapters removed. Suppose the remaining chapters are carefully arranged so that the story still appears coherent, characters seem to develop naturally, events appear connected, the plot makes sense. Unless you knew the missing chapters existed, you might never suspect that parts of the story were absent. The narrative would feel complete because your mind would automatically fill gaps and connect details into a meaningful whole. Human perception operates in a surprisingly similar way. An enormous amount of information exists around you. Light arrives from countless directions. Air carries subtle vibrations. Objects emit heat. Particles move through space. Electromagnetic signals pass through your environment. The amount of available information is so vast that no brain could process all of it simultaneously. If every detail entered conscious awareness at once, coherent experience would become impossible. Instead, the brain performs a remarkable act of selection. It filters, it organizes, it prioritizes, it is constructed. The result is a simplified model of reality that allows you to function effectively within the world. This model feels complete because the missing information never enters awareness in the first place. Consider vision. Most people assume they see their entire visual field with equal clarity. Yet this is not actually true. The sharpest vision occupies only a small region at the center of your gaze. Outside that region, detail decreases significantly. The brain compensates by constantly combining information from eye movements, memories, and expectations. The result is the experience of a stable visual world. You do not notice the missing detail because the brain continuously fills the gaps. Reality appears complete. The underlying information is not. The same principle extends far beyond vision. Your hearing filters sounds. Your attention filters events. Your memory filters experiences. Information is selected and compressed, yet the finished experience feels seamless. This tendency is not a flaw. It is one of the reasons human beings can navigate complex environments successfully. Without such filtering, the world would become overwhelming. The mind creates order from abundance. What makes this process fascinating is that science encounters similar patterns when studying the universe itself. Astronomers observe only a portion of the cosmos. Physicists measure only certain aspects of quantum systems. Cosmologists investigate only the observable universe. Yet from these limited observations, humanity constructs models that describe enormous portions of reality. These models are extraordinarily successful. They remain incomplete. The observable universe provides a powerful example. Everything humanity has ever observed beyond Earth exists within a region defined by the distance light has traveled since the beginning of cosmic expansion. This region contains hundreds of billions of galaxies and unimaginable quantities of matter and energy. Its scale is so vast that it exceeds ordinary comprehension. Yet according to many cosmological models, the observable universe may represent only a fraction of the total cosmos. Reality could extend far beyond what observation can reach. The visible portion feels complete because it contains so much structure. The hidden portion remains inaccessible. The completeness is experiential. The incompleteness is physical. This distinction becomes even more striking when we examine dark matter and dark energy. Together, these mysterious components appear to constitute most of the universe. Ordinary matter, the matter making up stars, planets, oceans, mountains, and living beings, accounts for only a small percentage of the cosmic total. The majority remains invisible. Scientists infer its existence through gravitational effects and cosmic expansion, but its true nature remains uncertain. Think about the implication. Most of the universe may consist of things humanity has never directly observed, and yet daily experience provides no hint of this hidden reality. The world still feels complete. The blind spot remains invisible because the visible portion functions coherently on its own. The same phenomenon appears in scientific measurement. Every measurement captures certain information while excluding other information. A thermometer measures temperature, but not every microscopic motion inside a substance. A telescope records incoming light, but not every process occurring beyond its observational limits. An equation describes patterns while simplifying countless details. These reductions are necessary because reality contains more information than any description can fully preserve. Science succeeds not by capturing everything, but by identifying the patterns that matter most. The result is extraordinarily powerful. It is also inherently incomplete. This realization leads to a profound philosophical question. How would we recognize an incomplete reality if the incompleteness itself remains hidden? Imagine living inside a vast maze while possessing access to only a few corridors. If those corridors contained enough variety and structure, you might assume they represented the entire maze. The unseen sections would never announce their existence directly. They would remain absent from experience. Reality may present a similar challenge. The universe does not arrive with labels indicating which information is missing. We encounter only the information available to us. Everything beyond that remains silent. The silence itself becomes difficult to detect because experience naturally organizes itself around what is present rather than what is absent. This is one reason scientific revolutions often feel surprising. Again and again, humanity discovers that reality contains layers previously hidden from observation. Microscopic worlds existed before microscopes. Galaxies existed before telescopes. Radio waves existed before radio receivers. Quantum phenomena existed before quantum theory. Each discovery revealed that reality was larger than the picture previously considered complete. The pattern repeats throughout history. What feels complete at one stage often proves incomplete at the next. This does not imply that knowledge is impossible. It suggests something more subtle. Reality may always exceed the models used to describe it. Every map leaves out territory. Every theory leaves out detail. Every observation leaves out information. Yet, because the remaining structure is coherent, the world continues to appear whole. The deeper scientists investigate, the more this pattern emerges. The universe does not merely contain hidden objects. It contains hidden layers of description, hidden relationships, hidden structures, hidden processes. Most remain invisible, not because they are distant, but because the information required to reveal them never reaches ordinary awareness. This creates one of the central mysteries behind the idea of a blind spot in reality. The blind spot may not look like a hole. It may not appear as an obvious absence. It may not announce itself in any dramatic way. Instead, it may hide behind the very completeness of experience. The universe may appear finished precisely because the mechanisms constructing our understanding are designed to create coherence from limited information. And if that is true, then the greatest challenge facing science is not simply discovering what exists, it is discovering what remains hidden behind the illusion of completeness. Because somewhere beyond the boundaries of observation, beyond the information available to measurement, and beyond the models currently used to describe existence, reality may continue in ways that remain entirely absent from the picture humanity has assembled. The universe feels complete. That does not mean it is, and the difference between those two ideas may be where the blind spot truly begins. Knowledge seemed straightforward. Something existed, and if a person looked carefully enough, they could learn about it. A tree stood in a field whether anyone observed it or not. A mountain remained where it was regardless of who happened to be watching. Reality appeared to possess definite properties, and observation simply revealed what was already there. This picture felt so natural that few people questioned it. The universe existed. Human beings observed it. Knowledge gradually expanded. The relationship appeared simple. Then quantum physics arrived and disrupted one of the oldest assumptions ever made about reality. At the quantum level, the connection between existence and knowledge becomes surprisingly difficult to define. The deeper scientists investigated atoms and subatomic particles, the more they encountered a strange barrier. On one side stood what could be measured and known. On the other side stood a deeper reality that seemed unwilling to reveal itself completely. The result was not merely a technical challenge, it was a fundamental limit on how knowledge and existence relate to one another. To understand why this barrier is so important, imagine trying to study a distant object hidden behind a curtain. You cannot see the object directly. Instead, you receive clues, you hear sounds, you observe shadows, you detect movements in the fabric. Gradually, you build a picture of what might be behind the curtain. Yet no matter how much information you gather, the object itself remains partially concealed. Quantum physics often feels remarkably similar. Scientists can measure outcomes with extraordinary precision. They can predict probabilities with astonishing accuracy. They can calculate behaviors that match experiments to many decimal places. Yet when they attempt to describe what reality is actually doing beneath those measurements, certainty begins to disappear. The equations work, the observations work, the deeper picture becomes difficult to access. This is where the quantum barrier begins to emerge. In classical physics, an object possesses properties whether anyone measures them or not. A ball has a position, a planet has a trajectory, a moving car has a speed. Observation reveals those properties but does not create them. Quantum systems behave differently. Before measurement, a quantum particle is often described by a mathematical object known as a wave function. The wave function does not describe a single definite state. Instead, it represents a range of possibilities. Only when a measurement occurs does a specific outcome appear. This creates a question that has fascinated physicists for more than a century. What exactly exists before measurement? The answer remains one of the most controversial topics in science. Some interpretations suggest that quantum systems do not possess definite properties until measurement occurs. Others argue that deeper variables remain hidden from observation. Still others propose that multiple outcomes coexist in ways that challenge ordinary intuition. Despite decades of debate, no consensus has fully resolved the mystery. What makes the situation extraordinary is that all of these interpretations successfully reproduce the observed results. The experiments agree. The deeper reality remains uncertain. This uncertainty reveals a remarkable boundary. Humanity possesses reliable knowledge about what can be observed. Humanity does not yet possess complete knowledge about what exists beyond observation. The gap between those two domains forms a kind of quantum blind spot. Consider one of the most famous examples in quantum physics. An electron can behave as both a particle and a wave depending upon how it is observed. Experiments repeatedly confirm this behavior, yet the electron does not neatly fit either category. When physicists attempt to imagine what the electron is doing between observations, ordinary concepts begin to fail. The electron appears real. Its effects are measurable. Its behavior is predictable. Its underlying nature remains difficult to describe. The barrier appears once again. Knowledge reaches a limit. Existence continues beyond it. The challenge becomes even more fascinating when we think about measurement itself. In everyday life, measurement feels passive. A ruler measures length. A clock measures time. A thermometer measures temperature. The measuring device records information without fundamentally changing what is being measured. Quantum systems refuse to cooperate with this intuition. At microscopic scales, observation becomes an interaction. To measure a particle, information must be exchanged. Light may be directed toward it. Energy may be transferred. The system becomes part of a larger process involving the observer and the measurement apparatus. As a result, the act of observation cannot always be separated from the outcome being observed. This realization transformed physics. It suggested that knowledge does not simply reveal reality. Knowledge participates in the process through which reality becomes accessible. The distinction may sound subtle, but its implications are profound. Imagine trying to examine a delicate snowflake using a source of intense heat. The very act of observation would alter the object. Information could only be obtained by changing the thing being studied. Quantum measurement often involves a similar challenge. Reality does not always reveal itself without interaction, and every interaction creates limitations. This limitation appears most clearly in the famous uncertainty principle. Certain pairs of properties cannot be known simultaneously with unlimited precision. The more accurately one property is measured, the less accurately another becomes known. This is not a failure of technology. It is not a temporary obstacle waiting for better instruments. The uncertainty appears woven into the structure of nature itself. Reality imposes boundaries on what knowledge can access. The existence of these boundaries suggests something remarkable. The universe may contain aspects that cannot be converted into complete knowledge, not because they do not exist, because existence and observation are not identical. This distinction sits at the heart of the blind spot mystery. Human beings often assume that reality consists of whatever can be observed. Quantum physics repeatedly suggests that reality may extend beyond what observation can fully capture. The barrier becomes even more mysterious when we consider quantum entanglement. When particles become entangled, their properties become linked in ways that appear to transcend ordinary expectations about space and separation. Measuring one particle provides information about another, even when enormous distances separate them. Experiments have confirmed these correlations repeatedly, yet explaining how the underlying connection operates remains difficult. The mathematics describes the relationship. The deeper mechanism remains hidden. Again, knowledge encounters a boundary. Again, existence appears to continue beyond it. Some physicists now suspect that information itself may occupy a more fundamental role in reality than matter or energy. In certain theoretical approaches, space-time may emerge from networks of informational relationships. The universe may not be built primarily from objects. It may be built from connections. If this idea proves correct, then the quantum barrier becomes even more significant. The blind spot may not merely separate observers from hidden particles. It may separate observers from the deeper architecture from which reality itself emerges. Imagine living inside a vast building while seeing only the rooms immediately around you. You could learn a great deal about the structure. You could map hallways. You could study walls and doors. Yet the foundational framework supporting the entire building might remain hidden behind surfaces you never penetrate. Quantum physics may be revealing a similar situation. The observable universe provides access to certain aspects of reality. The deeper framework remains partially concealed. The barrier does not necessarily mean that reality is unknowable. It means that knowledge may always encounter limits imposed by the structure of existence itself. This possibility carries profound implications. Scientific progress encouraged the belief that every mystery would eventually disappear. Given enough data, enough time, and enough intelligence, complete understanding seemed achievable. Quantum theory introduces a more nuanced picture. Knowledge continues to expand, yet some boundaries appear fundamental. The universe may permit access to certain truths, while withholding others. The blind spot may not be a temporary gap in understanding. It may be a permanent feature of reality, a boundary separating what can be known from what can only be inferred. And if such a boundary truly exists, then the mystery becomes larger than quantum mechanics alone, because the same barrier may appear wherever observation encounters its ultimate limits. The deeper scientists investigate, the more they discover that reality extends beyond the reach of direct knowledge, and somewhere beyond that quantum horizon, hidden behind the boundaries separating observation from existence, may lie regions of reality that physics can detect only through their shadows, regions that influence the universe while remaining forever beyond complete description, regions that form part of the blind spot itself. The most trusted assumption in human experience is the belief that causes produce effects. Every day of our lives reinforces this idea. A stone falls because gravity pulls it downward. A seed grows because it receives water, sunlight, and nutrients. A star shines because nuclear reactions occur within its core. The world appears to operate through an endless chain of relationships in which one event leads naturally into another. Cause comes first, effect follows afterward. The sequence feels so obvious that most people never stop to question it. Yet when physicists investigate some of the deepest regions of reality, they encounter situations where the relationship between cause and effect becomes surprisingly difficult to define. The universe continues to behave according to mathematical laws, but the familiar picture of straightforward causality begins to lose its clarity. Events remain connected, yet the nature of the connection becomes increasingly mysterious. This is one of the strangest blind spots in modern physics. Not a place where reality disappears, not a place where matter vanishes, a place where the very idea of what causes what becomes uncertain. To understand why this matters, imagine watching a row of dominoes fall. The sequence appears simple. One domino strikes the next, that domino strikes another. The chain continues until the entire row collapses. Every effect can be traced back to a previous cause. The relationship is visible and easy to understand. Now imagine examining reality at deeper and deeper levels. Causality continues to seem reliable. A force acts upon an object. The object responds. A reaction occurs. A consequence follows. Yet as physics moves toward extreme environments and microscopic scales, the clean sequence begins to blur. The first signs of this challenge emerged through quantum mechanics. In the quantum world, particles do not always behave according to the expectations formed by everyday experience. Instead of following perfectly predictable paths, they are often described through probabilities. A quantum system may possess several possible outcomes before a measurement occurs. Physicists can calculate the probabilities with extraordinary accuracy, but predicting a specific outcome in advance is often impossible. This creates a subtle but important shift. Classical causality suggests that complete knowledge of the present should determine the future. Quantum mechanics suggests that complete knowledge may still leave room for uncertainty. The effect remains connected to the cause. The connection no longer appears entirely deterministic. This distinction transformed the way scientists think about reality. Many researchers believed that the universe functioned like an enormous clock. If every detail were known, every future event could theoretically be predicted. Quantum theory challenged that picture. Nature appeared to contain an element of unpredictability built directly into its structure. The deeper question became unavoidable. If multiple outcomes remain possible until measurement occurs, what exactly determines which outcome becomes real? The answer remains one of the most debated questions in physics. Different interpretations offer different explanations. Some suggest that probability itself is fundamental. Others propose hidden structures beyond current observation. Still others imagine branching realities in which multiple outcomes occur. Regardless of interpretation, the mystery reveals a region where ordinary causality becomes difficult to describe. The uncertainty does not stop there. Quantum entanglement introduces another challenge. When particles become entangled, their properties become linked in ways that seem to transcend ordinary ideas about separation. Measuring one particle provides information about another, even when large distances separate them. Experiments repeatedly confirm these correlations, yet explaining the deeper mechanism remains difficult. The connection exists. The cause and effect relationship becomes harder to visualize. The universe appears to contain relationships operating beneath familiar intuitions about space and communication. For many physicists, entanglement represents one of the clearest signs that reality may possess structures hidden beneath ordinary observation. The blind spot appears not because the phenomenon is invisible, but because the deeper explanation remains elusive. The mystery becomes even greater when we turn our attention to black holes. Black holes occupy a unique position in modern physics because they push scientific theories toward their limits. Near a black hole, gravity becomes extraordinarily intense. Space and time themselves become distorted. Paths that seem straightforward elsewhere become increasingly difficult to interpret. As matter approaches an event horizon, strange questions emerge. How does information behave? How should outside observers describe events? What sequence of causes and effects remains valid? The mathematics continues to function, Yet the intuitive picture becomes increasingly uncertain. Inside the event horizon, the challenge becomes even more dramatic. Information cannot escape, signals cannot return. Observers outside the black hole lose access to what happens beyond the boundary. Cause and effect may continue inside. Knowledge of those relationships becomes inaccessible. This creates a remarkable situation. Reality continues to evolve. Observation loses the ability to follow the chain. The blind spot grows larger. Another fascinating example appears when cosmologists study the earliest moments of the universe. As scientists trace cosmic history backward toward the beginning, conditions become increasingly extreme. Temperatures rise, densities increase. Distinctions between familiar forces begin to disappear. Researchers approach a region where known theories cease to provide clear answers. The problem is not merely technical. The concepts themselves begin to struggle. Before spacetime acquired its familiar structure, what did causality even mean? How should causes be defined when time itself becomes uncertain? The question is difficult because causality depends upon temporal order. A cause must occur before an effect. But if the structure of time becomes unclear, then the framework supporting causality also becomes unclear. This possibility reveals something profound. Cause and effect may not be fundamental features of reality. They may emerge from deeper structures. Just as temperature emerges from the motion of countless particles, causality itself may emerge from more basic relationships hidden beneath spacetime. Several modern theories explore exactly this possibility. Certain approaches to quantum gravity suggest that spacetime may arise from networks of informational connections. If spacetime emerges from deeper processes, then temporal order may also emerge. In such a universe, causality would not occupy the foundation of reality. It would be one of the structures generated by deeper mechanisms. The implications are extraordinary. Human beings experience reality through sequences. Memories point toward the past. Expectations point toward the future. Every aspect of ordinary life depends upon causality. Yet the universe may operate according to principles that exist prior to the appearance of causal order. The familiar chain of events may represent only one layer of a much larger system. This idea becomes even more intriguing when we consider the limits of observation. Whenever scientists identify a cause, they rely upon information connecting events. Information must travel, measurements must occur, relationships must be reconstructed. If information becomes inaccessible, causality becomes difficult to verify. The connection may still exist. Observation can no longer confirm it. This means that uncertainty about cause and effect often emerges wherever information encounters limits. The pattern appears repeatedly throughout modern physics, quantum systems, black holes, cosmic horizons, the earliest universe. Again and again, the universe presents situations where causal relationships remain partially hidden, not because nothing happens, because the information required to fully understand what happens cannot always reach us. The deeper scientists investigate, the more they encounter a surprising possibility. The universe may contain regions where causality itself behaves differently from anything experienced in everyday life. Regions where ordinary distinctions between before and after lose their simplicity. Regions where observation captures outcomes while missing the deeper processes connecting them. Regions where reality continues to function even as human understanding struggles to follow. And that realization carries us closer to the heart of the blind spot. Because if there are places where cause and effect become uncertain, then there may also be places where reality extends beyond the concepts physics currently uses to describe it. Places where existence continues while our explanations begin to fade. Places where the universe remains real even when our understanding no longer keeps pace with it. And beyond those regions may lie an even larger possibility. The possibility that reality itself extends beyond what physics can currently describe. Throughout the history of science, one belief has quietly guided humanity's search for knowledge. It is the belief that reality, no matter how strange it may appear, can ultimately be described. New discoveries may require new mathematics. Unexpected observations may force old theories to be revised. Entire worldviews may collapse and be replaced by better ones. Yet beneath all these changes lies a powerful assumption. The universe is understandable. Reality may be difficult to explain, but eventually the correct description can be found. This assumption has been remarkably successful. When planets behaved in unexpected ways, better theories emerged. When electricity and magnetism appeared mysterious, deeper principles were discovered. When atoms revealed structures hidden within them, physics expanded to include entirely new layers of reality. Again and again, nature appeared complicated until the right framework revealed an underlying order. This history naturally encourages confidence. Every mystery solved seems to suggest that future mysteries will also be solved. Every successful theory strengthens the belief that reality can ultimately be described through science. Yet modern physics has uncovered a possibility that is far more unsettling. What if reality extends beyond what any physical description can fully capture? What if the blind spot is not merely a temporary gap in knowledge? What if it marks a boundary between the part of existence that can be described and a deeper region that resists description altogether? This idea may sound like surrender. It may sound as though science is giving up. In reality, it emerges directly from some of the most successful scientific discoveries ever made. The deeper researchers investigate the foundations of existence, the more frequently they encounter limits. Not practical limits, not technological limits, conceptual limits, boundaries where the language of physics itself begins to lose clarity. Consider the role of mathematics. Physics depends upon mathematics because mathematics provides a precise way to describe patterns. Equations predict planetary motion. Equations describe electromagnetic fields. Equations explain the behavior of atoms, stars, and galaxies. Mathematical structures have become so successful that many people assume reality itself must be fundamentally mathematical. Yet mathematics is ultimately a language. It is an extraordinarily powerful language, but it remains a language nonetheless. Every language possesses strengths. Every language possesses limitations. Imagine trying to describe a symphony using only geometry. Certain aspects could be represented, patterns could be identified, relationships could be mapped. Yet the experience of hearing the music would remain beyond the description. The map would contain information. The experience would exceed the map. Some physicists and philosophers wonder whether reality may contain aspects that relate to our theories in a similar way. The descriptions may be accurate. The reality described may still be larger than the description itself. This possibility becomes especially interesting when we examine quantum mechanics. Quantum theory remains one of the most successful scientific achievements in history. Its predictions have been tested repeatedly with astonishing precision. Yet despite its effectiveness, physicists continue debating what the theory actually says about reality. The equations work. The measurements work. The interpretation remains uncertain. Different explanations often produce identical predictions. This creates a remarkable situation. Science can describe outcomes with extraordinary accuracy while remaining uncertain about the deeper reality generating those outcomes. The blind spot appears not in the data. The blind spot appears in the connection between description and existence. Reality behaves in ways that can be calculated. Understanding what reality actually is becomes more difficult. The same challenge appears in discussions of space-time. For generations, space and time were treated as fundamental ingredients of existence. Then relativity revealed that they form a unified structure. More recently, some approaches to quantum gravity suggest that space-time itself may emerge from something deeper. If this idea proves correct, then one of the most important concepts in physics may not be fundamental after all. Space may emerge, time may emerge, geometry may emerge. The framework used to describe reality may itself be a product of deeper processes. This raises an extraordinary question. If space-time emerges from something more basic, What language should be used to describe that deeper level? The familiar concepts may no longer apply. Distance may lose meaning. Location may lose meaning. Duration may lose meaning. The deeper reality may operate according to principles for which human intuition possesses no direct equivalent. And if our conceptual tools emerge from the very structures we are attempting to explain, then certain aspects of reality may resist complete description. The challenge becomes even more profound when we think about observation. Everything science knows comes through observation. Every theory is built from measurements. Every measurement depends upon information. Every piece of information arrives through interactions governed by physical laws. This means that science studies reality through a specific channel. The channel is powerful. The channel is limited. If some aspects of existence never generate observable information, then those aspects may remain inaccessible to physical investigation. This does not mean they do not exist. It means they do not participate in the observational processes upon which science depends. Imagine standing inside a vast building while only a handful of rooms are illuminated. You can study those rooms carefully. You can measure them. You can understand their structure. You may even infer details about the larger building. Yet the darkened regions remain beyond direct inspection. The building is larger than the illuminated portion. Reality may be larger than the observable portion. The possibility becomes even more fascinating when we consider consciousness. Human experience occupies a unique position within the universe. Every scientific observation ultimately becomes meaningful because conscious beings interpret it. Measurements acquire significance because minds understand them, yet consciousness itself remains one of the least understood phenomena in existence. Neuroscience has revealed enormous amounts of information about the brain, but the relationship between physical processes and subjective experience remains deeply mysterious. How does matter become experience? How does neural activity become awareness? Why does reality feel like something from the inside? No consensus answer exists. The mystery persists despite decades of investigation. For some researchers, this suggests that reality may contain layers not fully captured by current physical descriptions. Whether this idea ultimately proves correct remains uncertain. What matters is that the question exists, even within one of the most familiar aspects of existence, our own awareness. Reality continues to resist complete explanation. The pattern appears repeatedly. Black holes reveal informational mysteries. Quantum mechanics reveals interpretational mysteries. Cosmology reveals observational boundaries. Consciousness reveals experiential mysteries. Again and again, reality seems larger than the frameworks used to describe it. This does not imply that science is failing. It suggests something far more interesting. The universe may be deeper than any single description. Each theory reveals part of the landscape. No theory necessarily becomes the landscape itself. Every map captures certain features. No map becomes the territory. The blind spot emerges wherever the territory extends beyond the map. Future discoveries will shrink that blind spot. New mathematics will reveal hidden structures. Deeper theories will unify ideas that currently seem unrelated. Scientific history provides many reasons for optimism. Yet even if understanding continues to expand, another possibility remains open. Reality may always exceed the descriptions used to explain it. The universe may not fit entirely inside any conceptual framework created by the minds attempting to understand it. And if that possibility is true, then the blind spot is not merely a region waiting to be explored. It is a reminder that existence is larger than observation, larger than measurement, larger than theory, larger than the language through which human beings attempt to describe it. Somewhere beyond the boundaries of current physics, beyond the limits of observation, and beyond the reach of concepts that presently define understanding, reality may continue unfolding according to principles we have not yet imagined. Principles that shape the universe while remaining invisible to the frameworks used to study it. Principles that belong to a deeper layer of existence, a layer that may already surround us, influence us, and sustain the reality we know, while remaining hidden beyond the edge of what physics can currently describe. After exploring cosmic horizons, hidden information, quantum uncertainty, inaccessible regions of space-time, and the possibility that reality extends beyond current physical descriptions, we arrive at the final lesson hidden inside the blind spot. It is not a lesson about galaxies, black holes, particles, or equations. It is a lesson about ourselves. More specifically, it is a lesson about the limits of human understanding and the strange relationship between the mind and the universe it attempts to comprehend. Throughout history, humanity has often imagined knowledge as a journey toward completion. Each discovery appeared to bring us closer to a final picture of reality. New theories replaced old ones, new instruments revealed hidden worlds, new observations expanded the boundaries of understanding. The process seemed to move in a single direction. The unknown gradually became known. Yet every major scientific breakthrough has produced an unexpected consequence. Each answer created new questions. Each discovery revealed new mysteries. Each expansion of knowledge exposed larger regions of uncertainty. The horizon never disappeared. It simply moved farther away. This pattern is so consistent that it forces us to reconsider a fundamental assumption. Perhaps the purpose of knowledge is not to eliminate mystery. Perhaps the expansion of knowledge simultaneously expands awareness of what remains unknown. The blind spot in reality reveals this pattern more clearly than almost any other scientific idea. The blind spot appears to be a problem waiting to be solved. It seems like a hidden region that future generations will eventually understand. Better instruments will be built, better theories will emerge. The missing pieces will be found. This may happen in some cases. History provides many examples of mysteries that eventually yielded to investigation. Yet the blind spot also reveals something deeper. Some limits do not arise because information has not yet been collected. Some limits arise because the observer is part of the system being observed. This distinction changes everything. Imagine a character living inside a novel, attempting to understand the entire book. The character could learn about events occurring nearby. The character could discover patterns and relationships within the story. Yet the character would face a fundamental limitation. The book itself exists at a level beyond the character's direct access. The character is inside the system. The full structure lies beyond the perspective available from within it. Human beings may face a similar challenge. We attempt to understand the universe while existing inside the universe. Every observation occurs from within reality. Every measurement occurs from within reality. Every theory is created by minds that are themselves products of reality. The observer and the observed are inseparable. This situation creates a remarkable possibility. Some aspects of existence may remain difficult to understand, not because they are complicated, but because they occupy a level of reality that cannot be fully accessed from within the system itself. The challenge resembles trying to see your entire field of vision without using a mirror. You can observe countless objects. You can study the world around you. Yet certain aspects of the system remain hidden because they form part of the framework through which observation occurs. The blind spot may represent something similar, not merely a missing region of information, a hidden feature of the relationship between knowledge and existence. This idea becomes more intriguing when we consider the evolutionary origins of human perception. The human brain did not evolve to reveal objective reality in its entirety. It evolved to support survival. Our senses detect information useful for navigating the environment. They identify patterns relevant to finding food, avoiding danger, and interacting with other living beings. Nothing in evolution requires the brain to reveal the deepest structure of existence. A useful representation may be more valuable than a complete one. Imagine a pilot navigating an aircraft using an instrument panel. The panel does not display every detail about the airplane. It provides selected information necessary for effective operation. The simplified display is useful precisely because it excludes overwhelming amounts of detail. Human perception may function in a comparable way. What we experience as reality may be a highly effective interface rather than a complete representation of existence. The universe appears solid, continuous, and understandable because those features allow meaningful interaction with the environment. The deeper architecture may be far more complex than the experience presented to consciousness. consciousness. If this possibility is correct, then the blind spot becomes unavoidable. Reality may contain structures that never appear within ordinary perception, because perception was not designed to reveal them. Science extends perception through instruments and mathematics, but even scientific investigation remains constrained by the cognitive tools available to human minds. This realization does not weaken science, it strengthens it. One of the greatest achievements of science is its willingness to recognize limitations. Scientific progress often begins when researchers identify assumptions that previously went unnoticed. The recognition of limits becomes a source of discovery. The blind spot continues this tradition. It reveals that some boundaries belong not only to technology, but also to understanding itself. Another clue comes from mathematics. Mathematics has proven extraordinarily effective in describing physical reality. The precision with which equations predict natural phenomena remains one of the most astonishing facts in science. Yet mathematics also reveals its own limitations. Certain mathematical systems contain truths that cannot be proven within the systems themselves. Some questions remain undecidable. Some structures contain boundaries that cannot be crossed using the rules available inside them. These discoveries suggest a fascinating possibility. Limits may not be accidental features of knowledge. Limits may be fundamental aspects of complex systems. If this principle applies to mathematics, perhaps it also applies to reality. The universe may contain questions that cannot be answered from within the framework available to observers living inside it. The blind spot may represent one manifestation of this deeper principle. The mystery becomes even more profound when we consider scale. Human beings occupy an extremely narrow range of existence. We live between the microscopic world of quantum phenomena and the enormous scales of galaxies and cosmic expansion. Our lifetimes occupy only a tiny fraction of cosmic history. Our bodies interact with only a narrow range of energies and distances. Yet from this limited position, we attempt to understand the entire universe. The achievement is extraordinary. The challenge is equally extraordinary. Imagine an ant attempting to understand the structure of an entire continent based solely on the ground beneath its feet. The ant may discover meaningful patterns, it may learn important truths, yet enormous aspects of the larger structure would remain inaccessible. Humanity may occupy a similar position. Our understanding continues to grow. Reality may remain vastly larger than the perspective from which we study it. This possibility explains why the blind spot carries such profound significance. It is not merely another unsolved scientific problem. It is a reminder that knowledge has boundaries, a reminder that observation has boundaries, a reminder that explanation has boundaries. The universe repeatedly demonstrates that reality extends beyond whatever picture we currently possess. Every generation inherits a model of existence that feels comprehensive. Every generation eventually discovers hidden layers beyond it. The process continues. The horizon recedes. The blind spot remains. Yet there is something deeply inspiring about this realization. The limits of understanding do not diminish the value of knowledge. They give knowledge meaning. If reality were fully transparent, discovery would end. Curiosity would lose its purpose. The search for understanding would become unnecessary. Instead, the universe presents a different invitation. It reveals enough to encourage exploration, while withholding enough to preserve mystery. The blind spot stands at the center of that relationship. It marks the place where understanding encounters its frontier, not a wall, not a failure, a frontier. A reminder that existence remains larger than any theory, larger than any observation, and larger than any framework through which human beings attempt to describe it. And perhaps that is the deepest lesson hidden inside the blind spot. The universe is not simply waiting to be solved like a puzzle. It is an evolving landscape of discovery whose horizons continue moving outward as knowledge expands. Somewhere beyond the limits of observation, beyond the reach of measurement, beyond the boundaries of current theories, reality continues its existence without concern for what humanity understands about it. And that realization may be more valuable than any answer. Because the blind spot does not merely reveal what we do not know, it reveals how much more there may be to know. The search for knowledge has carried humanity across oceans, through space, and deep into the structure of matter itself. Yet every discovery has revealed another horizon waiting beyond it. The blind spot in reality is not merely a missing answer. It is a reminder that the universe remains larger, deeper, and stranger than any theory we create. Somewhere beyond the edge of what can be observed, understood, or measured, reality continues without our permission. And until that hidden region gives up its secrets, one question will remain unanswered. How much of existence are we still unable to see?